So hello, this video is a quick explanation of how to create an Esprit program for your ME3820 5-axis lab. We'll be going through creating the machine setup, how to save the machine setup, how to save the program as a template so you can come back and just work straight from here if you ever want to create a new 5-axis program. And then we'll be going through creating a couple different operations so you can actually do some machining. So we're going to start from the mini-mill template. And now what we want to do is tell Esprit that we have a 5-axis machine rather than a normal 3-axis machine. So we're going to go to Common Machining. Let me deselect it so you can see me select it. So Common Machining right here. Then Machine Setup. Program number you can change to anything less than 7,000 that you want to. We'll go with 3820 just because. Program name you can change as you wish. NC code output settings controls what post the Esprit uses by default when it's posting your code, so we're going to add the 5-axis post as default. Start position, just leave alone. The rotary retract movement, just leave alone. Over here under miscellaneous, since we're on the VF or VM, depending on what you're using when you do this lap, we're going to make the maximum RPM 12,000 rather than 6. As always, make sure dogleg rapid is on. And now we can come down to the 5-axis mode. Leave the RTCP coordinate mode as fixed. If you want to read more about what that is, go see the 5-axis machining at WPI document on the Manufacturing Lab SharePoint or see the Esprit help. And check the Calculate Links button. In short, the Calculate Links just tells Esprit to actually create link moves between the different cycles that will occur during your operation. Click the Settings button. That'll pop up this window, 5-axis external rapid links. It's just what links should I be using when creating the operation. So the first one we're going to select is feed bridge. This is just going to connect different moves using feed moves instead of rapid moves. And then we're going to add table 3 steps. Table 4 steps just allow Esprit some options for what it wants to use when creating transitions. So click OK, and that's the general tab of the machine setup. Moving over to assembly, this is where we're going to actually define the 5-axis. So our T5C mounts to the table, so we actually need to add the axes to the table. So we're going to expand, believe it or not, the table category. Notice there are no X or Y axes defined here. That's because whenever you're in solid mill, Esprit automatically assumes an X, a Y, and a Z axis, so they don't need to be defined, not even once you add an A or B axis. But we're interested in the rotary axes, so we're going to add those now. The first one we're going to add is the A axis, so make this drop down A and click New Axis. Leave the label alone. Leave the type alone. It's a rotary axis. It should be a rotary. Axis point XYZ, that corresponds to where the rotary axis is in relation to the global XYZ coordinate system. It is very important to get that right. It will not be 0. However, you're going to need to wait until you're on the machine to actually measure that. So for now, you can just leave it as 0. Axis vector, it just tells Esprit what direction the axis is pointed in. It turns out that if you were to go up to the machine, handle jog the rotary axis, and then use the left hand rule on that axis, you'd find the correct vector. So our axis is oriented along, parallel to the x-axis, and if you handle jog it in a positive direction, it'll jog to the back of the machine. So apply left hand rule to that. That will give you x equals 1, y equals 0, z equals 0. Minimum position and max position are there to limit the angular rotation of the axis. We're going to make the minimum negative 110 degrees and the max 10. That's going to tell us Esprit to allow the rotary axis to come 10 degrees towards us from the top and to go backwards 110 degrees at maximum. So that's the A axis. So now we have a 4-axis machine, but we're interested in 5. So we're going to add the 5th axis. It's going to be a B axis, and just click New Axis again now that you have B selected. Leave the label alone again, leave the type alone. Axis point XYZ, we're going to actually line up our axis with the XYZ coordinate system, so this is going to be 0 this time. Axis vector, if you perform the left-hand rule on the axis will rotate counterclockwise if you're looking at it from the positive Y direction, and it's lined up along Y. So left-hand rule, X is 0, Y is 0, C equals -1. And then we're going to leave minimum as 0, max as 360. What that does, it does not actually tell Esprit that the axis can rotate 360 degrees. It actually tells Esprit that the axis can rotate infinitely. If you wanted to restrict an axis to 360 degrees, put in 359.9999999. So that's your machine setup. I'm going to change the comment because it's not the mini-mill template anymore. So how does 5-axis ME3820 seem? Okay, so go ahead and click OK. Your machine setup is done. So, thing I forgot to tell you before exiting out, you wanted to save your machine setup, so we're going to do that now. So go back to machine setup, and if you just right click in the gray area and click save, you can save the machine setup as is. So ME3820 5-axis, and click save, click OK, because now you are actually done, I hope. Sorry if you're not. And now we're going to move on to the next step. We're going to add any more tools that we want. We have a 3/8 drill mill, the 1/4-inch end mill, the 3/8 end mill, and the normal face mill that you get from M1800. If you want to add any more tools, go right ahead. Do that now before you save it, the template. And also go ahead and double check that collision detection is set to full, because, well, you want to make sure you catch those crashes. So now we're going to actually save this file as a template. So go File, Save As, and where it says Save As Type, change that to Esprit template files. I'll just save it to the desktop for example, and go ahead, change your name to whatever you want the name to be, and click Save, and you've just created your 5-axis template. Before going on, if you do not create a new file from that template, you are going to change the template you just saved instead of creating a new program. So click File, go to wherever you just saved that template, and open it up. And if you look carefully, this has now become a .esp instead of a .est, meaning that we're actually creating a program instead of a template now. Okay, with our template created, we can now go ahead and bring in our solid model. So as always, open, check merge, and just give me a second to reach it. Okay, I'm going to go to isometric just so I can see what orientation it came in. Go ahead and move it as necessary. I'm going through this real fast because you should all be experts at this now. And okay, now we're ready to start creating our chains and our definitions and our freeforms. So the first operation you're going to need to do is actually rough out this shape around here. So using the same techniques you've always used, we can just do this as a straight up 2.5 axis op. So we're just going to chain around this bottom, excuse me, like so. And then I'm actually going to go a little creative. I'm going to mask the solid here. And I am going to draw lines like that. And like that. You'll see why I'm doing this in just a second. And then we'll put a point on the intersection of those two lines. Now, I'm going to go ahead. Oops. And remember, Control-Z undoes. So I'm going to go ahead and move that line up to the, move that chain, sorry, up to the top of the part just so it's easier to work with. So now since I have 2 points, I'm going to use 2 points. Select the start height, select the bottom height, and now that chain is at the very top. If you want to leave it at the very bottom and make your op, go right ahead. I just chose to do it this way. I don't really care how you do it. It's your program, your operation, your choice. So I'm just going to write a contouring op to face off the sides here. So to ID, I'll just use our 3/8, 12,000 since we're on the VMVF, and get your speeds and feeds as you need them. I missed a 0 there. And watch pressing enter there. So you've got that. Check your strategy. Spiral move, yes, as always. Show the depth. And which side do we want to offset? Left. Advanced. And I like using radius, so I'm going to set that to radius. And now, as always, we're going to want to check that operation, make sure we're not crashing. So go to simulation. We'll create simulation stock now. So create stock from cylinder, outer radius 1/2. This is going to be one of those 1-inch diameter parts. Start at the origin, go down 3.5 inches. And yes, I did that right. So add, okay. I'll just fast forward to double check I did it right, which I did, and click play to actually see the op, and we ran fine. So we're going to stop this. Now we can actually get into the interesting part of doing the 5-axis operations. So the first operation you're going to want to make is your 2.5 axis operation you're going to use to machine one of these faces. So the way you're going to want to do that, the trick in doing that is going to be to control your tool orientation. Back when you only had 3 axes, tool always came from one angle. Now you have rotary axes, the tool can come from just about any angle. And the trick is, as I just said, control that orientation. The way that's done is using work planes. You go look at the Spree help and the 5-axis machining at WPI document for more about them. I highly suggest you do that. They're going to end up so helpful, but for now I'm just going to do the quick thing. So I'm going to reveal the work planes toolbar. So right click on your toolbar, go down to modify work plane, and I like putting it right there. So this first one is work plane from geometry. I'm going to select it, select the face. It puts a work plane at that face, and if I open up the work planes dialog and click new, and this looks like the left face of me. I like including the view just because I do. So we'll click OK, and now we can come back to this work plane. The thing to note about work planes that I'll tell you now, they control the orientation of the tool for any operation created on the feature that was created while that work plane was active. So currently what's active, now that I've made it active, is the left face. If I were to create the chain right now and then put a pocketing knob on that chain, the tool would come down nice and square to that surface as you're used to. If I were to make the chain now, then go change the work plane as I just did and make the operation, it would still work fine. Let me go back to the first place. If I went back and changed the work plane, then made the chain, everything's going to be screwed up. So just watch your work planes. We're going to start with the left face, because we're doing the left face, and we're just going to chain the perimeter of this because we're going to pocket it. So we've got our chain, and we'll rename that so we don't go insane with all the features we're going to have. And I'm going to make that open because I want an open pocket. And as always, make sure to catch every edge of your open chain. And now I'm going to go ahead and create pocketing up on that face. Same way you always create a pocketing up. Nothing really different once you've defined your chain on the correct work plane. Alternate cut direction, no. Morph move as always. Spiral as always. Smooth sharp corner as always. Extra moves as always. Total depth is going to be 0. That'll put us right at our chain, which is the bottom of the hole. Starting depth I'm going to leave at 0 because I know the greatest height you're going to see is 1/4, so it's fine. Open edge, all this stuff, just you've already worked with this, just do the same thing you've always done. Rough, enter your feeds and speeds. Same thing as always. Step over, same as always. Entry exit, same as always. I like using 4 degrees for the ramp angle. I really do not suggest using anything much greater. And then you can go to links and just same as always. So you might be able to see that operation we just created. You might already be lost in all the toolpaths. So I'm going to go to isometric to help you see. The one we just created is this triangular shaped one. To hide toolpaths, because you are going to want to do that eventually, you can of course hide it using the masks dialog, or you can go up, right click on each operation individually and click hide. That will just hide the toolpath so you can see what's going on. And back to let's check what we did with that operation, see how well it works. So we're just going to simulate the entire thing at full speed. And that's a slight issue. We can fix that, however. Let's just double check how that's crashing. Well, that's interesting. Okay, so it's crashing after making the transition before reaching its final place. Let's stop this. And we're just going to increase our clearance. We'll just make it 1 inch, just so that we know we're clear. And let's go ahead and simulate from the beginning, not just that one up again, and make sure we're good this time, which we are. Okay, so that's a 2.5 axis up. So we're going to go ahead and create your second operation, the swarf operation now. It's going to actually be a continuous 5-axis operation. You can reach it by either going to machine, solid mill mode 5-axis, and use either of those. Or you can actually reach all the solid mill mode operations through there, and then it's those two. So, sorry again, swarf's operations require different inputs depending on whether you're using the rolled swarf or the surface swarf, as you might imagine. I'm going to use the rolled swarf just because I found I like it more a little. The primary difference between the two is that the rolled swarf requires what's called a rolled feature. The surface swarf, on the other hand, does not. If you're wondering what a rolled feature is, hang on about 30 seconds. Okay, so the first input you need for a swarf is going to be your freeform. So create new freeform. We're going to call this front face. For a part, the only thing we want to machine is that face. We're going to leave the check empty because it's not actually going to touch any of this, so we're not going to make Esprit do the math to see whether it's touching. For the stock, you're probably all used to, you have to create an STL file, merge it into Esprit, and then use that file as the stock. It turns out that if you leave the stock box empty, Esprit will just use the simulation stock as stock and use that to do the math. And when I say simulation stock, let me click OK here so I can show you. When I say simulation stock, remember how we define simulation stock? I'm in simulation. So that's your simulation stock. And it doesn't look like just a cylinder anymore. So we could save it out of the program and save it back in. Kind of tedious. Or we just did what we did, which stopped the simulation, which just leave the stock box empty and it will use the state of the stock as it was at that point. The next thing the rolled swarf is going to require is a rolled feature. So go back to create and edit features and select rolled feature. We're going to call this front face. Cutting side should be right, probably. We'll fix that later if we want to. And we're going to recognize from solid faces. So faces, we're going to click select that same face again. For the lower edge, just select the lower edge of the part and click OK. And did I get, yes, I got the right direction correct. You can see by that arrow down there. So that's what we need to actually create the operation. So select the freeform and then go select 5-axis rolled swarf milling. Tool selection, use the 3/8 as you have as always. Speeds and feeds, 12,000 RPM, 3.5 hour rev, 80% plunge feed rate. Enable RTCP, yes, always do that. It will not post right if you don't. Tool path, tolerance, I'm going to knock that down to 1,000, stock allowance as you wish. Limit distance between points. See the Esprit help for what that does, or I'm just going to leave it as no. Rolled feature, select the rolled feature you just created. Cutting side should be right. Offset tool radius, yes. Stop at floor. Basically what that does is should Esprit allow the tool to go past the bottom of the surface. In this case, we do want it to go past so we can actually get all this material down here. In some cases, you're going to have material down here that you do not want to cut, which is why you'd stop. We're going to set single cut as no, because we don't actually want. Actually, we're going to set single cut as yes, because I didn't understand what that was. Loop around corners, we don't have any corners, so it doesn't really matter. And then all of this, use defaults. Links, retract optimization, just set it as full. Leave your clearance as 1,000. Approaches, same thing, they are as you've always seen. Just set up the approaches you want. I like radius and lateral plane and then radius. Rapid links, we're going to do the same thing as we did in machine setup. We're going to start by allowing Esprit to use a feed bridge, so connect different feed moves with more feed moves. It's going to be the most controlled option. And then we're going to do table, 3 steps, and table forceps. For exactly what each one of these is, go ahead and look at the spree help. The quick version is connects everything with feed moves, connects everything without moving the rotary axes much, and connects everything without moving the rotary axes much while deseparating the linear and rotary moves. Something I did not say before, you should not use any rapid links other than these three during a 5-axis operation while you're here. It just turns out that all of these, that one, these three, and that one are really all designed for tilting head and head table machines. We have a table machine, so just don't use those. So going over to collision detection, check and report collisions, shank clearance, holder clearance, you can just leave those set to 0. So go ahead, click OK, and the spree goes ahead and creates that toolpath. So let's go ahead and see how it works. It looks fine. So moving on to the 5-axis composite operation. Once again, the primary input needed for the 5-axis composite is a freeform. We're going to be machining the 2 remaining faces. So freeform, select that face, rename right and back faces. Check, as I said, don't want to make a spree do the math. Stock, we'll just let it pull the simulation stock. So click OK. Okay, so with your freeform operation created, we're going to go ahead and create the actual, with your freeform feature created, we're going to go ahead and create the actual operation. I'm going to use 5-axis composite. It's not the only way to do it, but it's one way to do it. Tool selection, feeds and speeds, as always. RTCP GS as always. Toolpath, machining pattern. We're going to leave it as parametric pattern. The short description of what it is the way a spree wraps a mesh around the surface to determine how to move the tool. As I said, I'm going to use parametric pattern. See the spree help for more. Drive surface, that's just that's just a face that a spree is going to use to do math to figure out how to orient the tool. Make sure it's a face that's within the freeform. I'm going to select that face. Tolerance, we're going to knock it down to 1 thou. And then you can leave all the rest of this as the default. Orientation, set normal to model. There are other options. You need to define more geometry to figure out how to do it, and you are told to keep the tool perpendicular to the face, so we're just going to use normal to model. Enable auto tilt. It won't make a difference in this op, but what it does allow normally is it just allows the tool to rotate relative to where it's supposed to be to avoid collisions. Links, same things as we've done before. Feed bridge, table 3 steps, table 4 steps, collision detection, check and report as always. So go ahead, check, see how that works. And we're crashing. That looks like we're crashing on the transition. So let's go look at our approaches, radius. Let's make that 1/2 inch, see what that does. And we appear to be fine. Okay, so go ahead, stop that. Save the entire thing. Simulate the entire thing. Now you can save the entire thing. And that's your lab. Now go ahead and machine it.